All right, so we are into our last 12 lectures of the semester. Last 12. Semester's pretty much over. So, looking ahead, this is today. Today's the 6th. We'll have a group quiz on Friday, and you have mastering due that day. On Monday, individual quiz mastering. Then, in, let's see, 1, 2, a little over 2.5 weeks, we'll do exam 3, which covers, let's see what chapters that would be. Chapter 5, 6, and the rest of 4. This is right. Yeah, so I think I have my mastering set up. So it's those 2 days. 15, 18. I think that's right. Exam 3, and then, oh, that's on the wrong day. That shouldn't be on the 25th. Should be individual quiz on the 2nd, 4th, 6th, and your final. And your final is cumulative and standardized. So you can be mentally getting ready for that. So all the multiple choice stuff will be what's on your final. It's more of a multiple choice test. So, questions about our schedule? Yeah. Sure. The final exam is cumulative and standardized. Any questions? I believe it is 75 questions, and you get 2 hours. Yeah. Yeah. Well, some of them are going real fast, like real obvious. And other ones, you just won't know, so you just skip them. Like, you're right. You're like, I have no idea. Circle something and keep going. Yeah.
And it's worth 100 as well? It's worth the same?
Yeah.
Okay.
But it's a little funky because it is standardized, and so I have to curve it. Like, there's no way that an average class overall does as well as every other college in the world, their average. So I move our average to the average.
For better or for like what?
Is typically you do as well on the final exam as your average of the other 3 exams. So if your other 3 exams, you've gotten an 80 on it, typically most people get an 80 on the final. That's how I try and work it out. So it's for your benefit. Rarely is a penalty. Only if you totally blow off the final exam will you do worse on the final than you do on the first 3 exams. So, yeah.
Is this a test where we should guess or should we not guess?
Guess. If you don't know it, make a good guess and move on to the next question. It's one of those. Yeah, Stephanie.
Is it all multiple choice?
Mm-hmm. And for some people, that's great. They're really stellar multiple choice guessers. Some people are not great multiple choice guessers. And so that's why I try and make it so that it's not a penalty to have an all multiple choice test. It's just, in theory, it's getting you ready, right? Because the MCAT's all multiple choice. The PCAT's all multiple choice. The GRE is all multiple choice. So if you're thinking about going on to graduate school in any form, is a multiple choice test, standardized. And so just try and get you into the mentality of being able to do a multiple choice test. So. All right, we're ready for, we have one last problem left over in chapter 5. That's pretty much like you did on the homework. And then we'll move on to chapter 6. Let me get my notes together. So they want you to calculate, oh, and I have your tests to give back to you, because everyone has taken the test who's going to take exam 2. So I can give those back to you in class.
What was the average for the test?
81.5. So, pretty good. Pretty good. I think any average in the 80s is usually pretty good. So. All right, so we want to calculate the speed for oxygen and argon at 298 degrees Kelvin, and then figure out between the two of them which is the faster moving gas. Based on what you know about gases, which one do you imagine to be faster looking at your periodic table? Yeah, we would guess oxygen is the faster of the two gases, because even 2 oxygens is 32 and argon is 40. So we would guess oxygen is the faster gas. So let's see if that's true. So speed, this U RMS, which is the root mean squared, which really just means average. So it's the square root of 3 gas constant temperature divided by molar mass. The trick to this is that now our molar mass has to have units of kilograms per mole because of the way we've defined some of the other constants. So, right, usually it's in grams per mole. We just have to move it over to kilograms per mole. So, if the molar mass of oxygen is typically 32 grams per mole, how do I get it into kilograms per mole? Put 1,000 here on the bottom. I can't see what I'm writing. There we go. So 3.2 times 10 to the negative second kilograms per mole. And if we do the same thing, bless you, for argon. Good there, we just converted grams to kilograms. Nothing tricky so far. Let's do oxygen first. So 3 times the gas constant. And you notice that we're using a different version of the gas constant. We're using the one in joules. I'll explain why here in a second. That's because a joule is a kilogram meter squared per second squared. Realize I'm writing kind of tiny today. So that means my kilograms will cancel out nicely. All right, moles, moles, Kelvin, and Kelvin. So solving this, I now get I'll see that tricky math. So the trickier part of this is just units, not so much the actual numbers. Did anyone happen to double check that, make sure I'm right today? I'm assuming all these blanks there means you totally got it right. I know why you brought the calculator. Awesome. All right. And let's do the same thing for argon. So what was our prediction? Is argon going to be faster or slower? Should be slower. Let's see. So does that make intuitive sense that argon has a heavier mass, so its overall speed is slower? Mathematically true. Alright, any questions on anything we did in the gases? Anything about gas laws, ideal gas laws, kinetic molecular theory of gases, anything else with gases? Gases. Alright, in that case, let's move on to thermodynamics. I'm looking at energy transfer. Alright, so we're going to spend quite a bit of this first day looking at terms so we all have the same language of energy and energy transfer. So why we care about energy transfer is that all chemical and physical change has an energy transfer associated with it. And the most common energy we're going to look at, right, is heat. We're going to spend a lot of time talking about heat, either needing to heat something to get it to go, or the reaction releases heat. So we're going to spend most of our time looking at that form of energy. But there is a few things to talk about first before we get to heat. So energy is the capacity of something to do work. And then work is the result of a force acting through a distance. So for example, let's look at a billiard ball, I guess, in motion. Alright, so you're out there playing pool on your weekends and evenings. I don't know what other kids do these days. Crazy kids playing pool down the pool hall. maybe in the 1920s. So let's say your ball's in motion, right? And it's going across the table. It's going to eventually hit another ball if you aimed correctly. If not, if you're like me, it just hits the edge. And then you forfeit your turn. But if you're a really good pool player, you'll actually not only hit the ball you called, but just that ball. So that'd be good. So, let's say you got your ball in motion and hits another ball. I guess the first ball. The first ball, the one that you hit originally, has energy because it was in motion, right? You imparted some energy to it. It then took the energy, turned that into motion. When those two balls hit, we've now done work. In this case, the work done was a transfer of energy. So the big key to start off thinking about heat and work is that both heat and work are ways to exchange energy. So we can either heat something and it's going to gain energy from that way, or you could have a force act upon your molecular object, and that force is work, and that will change the energy. Because someone will lose energy, someone will gain energy. So those are our two starting points. There are a few different types of energy, which we've talked about before. We've also talked about kinetic and potential. There's officially 4 different types of energy. Kinetic is the energy associated with the object being in motion. And the opposite of that one is potential, right? The object has energy based on where it is. So either it's on the ground or you're holding it up in the air. That's potential energy. We also have thermal and chemical. And as the name implies, thermal is associated with the temperature. Not necessarily that it's hot, just that it has a temperature. So either it could get hotter or it could get colder. Or there's chemical energy, which is energy associated with the position of an electron around an atom. So depending on what energy transfer you are looking to do, some of these may be in play. Maybe all of these are in play. Right, so obviously chemical energy is going to be fairly directly related to thermal energy, that you can heat something, which could then force this electron to maybe make a bond, or maybe break a bond, or maybe become an ion, or something. And then kinetic and potential, we think of more as like big things, like things you can hold in your hand. So these kinetic and potential conceptually are more big objects, and thermal and chemical are more conceptually the little objects, but they all are interrelated. So let's look at our first law that deals with energy. which is otherwise known as the first law of thermodynamics. Now, the first law states that energy cannot be created or destroyed. Energy can only be transferred from one kind of energy to another kind of energy, which we talked about this probably in like the 4th or 5th day of class. But now we're going to be able to talk about it in terms of using energy to do work or to transfer heat. So, since we know that the first law is true, and that energy cannot be created or destroyed, it can only be transferred, if we know that energy is related to heat and work, if we can measure heat and work, which we can, then we can make predictions about what's going to happen with our chemical reaction. We can predict it will get hotter, we can predict it will get colder, we can predict a bunch of different things about it. So, we're going to use our first law and this relationship to kind of make some predictions. So, some more terms we're going to need to have in order to be able to make these predictions is the phrase internal energy. So, internal energy is the sum of all the kinetic and potential energies of all the particles that compose a system, or the system, or whatever you're talking about. It's all the possible combinations of energy that a system can have. And it is called a state function. When I say state function, I mean this. The value that we get, in this case the value for internal energy, only depends on the initial and final states of the system. It does not matter how you arrived at that state. So, most often we use the example of going hiking or mountain climbing, whatever you want to call it, that 2 or 3 different parties all start at the bottom of Mount Everest, and most of them get to like the first stage. Some of them decide, oh, I forgot something back to the bottom, so they go back down, and the second party heads up, and then they come back up to and then the third party gets all the way to the top, and the second one, oh, has to go back down and back up because someone got sick, and they come back up. At the end, they've all scaled Mount Everest. One group did it the more efficient and faster way. The other group took a bunch of different routes to get there. But in the end, you would agree that they all climbed Mount Everest and succeeded in that way. That is a state function that we look at just, they were on the ground, they made it to the mountain. However they made it between those 2 states, doesn't matter. Just initial and final states. So whatever analogy works for you, that's the best way to describe a state function. I guess I'll write this last thing up here. So the state of a chemical system
going to be defined by 4, I guess, categories, ways to measure it. So based on our ideal gas law, what is one way we can measure our system? Not everybody at once. All the screaming, I can't hear up here. Hurts my ears. All right, pressure would be a good one. Temperature. Concentration. And phase. Those are going to be our 4 ways to define what state our system is in. So, another way of thinking about the states of matter is, let's say you and your friend are both trying to blow up balloons for a birthday party. I'm terrible at blowing up balloons. It takes me several attempts to get enough air in there that I can tie it off. I have other friends, like 2 or 3 big breaths, tie it off no problem. I always get like almost to the tie off point, and then all the air escapes. I have to inflate it again, and then I just, for whatever reason, I'm not good at tying off balloons. I didn't learn that skill, I guess, in middle school. Whenever you learn that skill, I missed out on that day. And so, that is another state function, right? In the end, all the balloons are inflated. So all the balloons have a known internal pressure. They all have a known concentration or number of moles. Things like that. Right. Okay. So on internal energy change, we can write as, delta, which is change in, big E, which is energy. So it's the difference between the final and initial states. So mathematically, we would write it as the energy of the final product, which is, products, minus E of the reactants, which is our initial state. So it's the difference between final minus initial. So if I look at my chemical reaction here, let's say in my bare hands I could take a piece of coal and squish it together with oxygen and make carbon dioxide. I can't actually do that yet. Working on it. But let's say I was able to do that. And so I have my carbon and my oxygen as my reactants. The internal energy of carbon dioxide is less than that of the 2 reactants. And so overall, I have a negative internal energy change. So you may be thinking, that's weird. You lost energy. Where did that lost, quote unquote, lost energy go? Did I actually lose it? Right? I haven't lost it. Based on our first law, I know I've just actually converted it to a different form. So the system, which in this case is my chemical reaction, the carbon plus oxygen making carbon dioxide, has lost energy. But as my fancy diagram over here, notice how fancy it is, a box and an arrow in another box. As this fancy diagram shows, this loss of energy is a gain by what we call the surroundings. is the exact same up here. So I have a negative loss of energy by the system. That means that the surroundings for the universe to remain balanced as it gains the energy. Good there? Your yin and yang making sense? Everything's on balance? Okay? So how do we exchange energy between the system and surroundings? What are some ways that we can do that? This picture's real small. Sorry. If you have it in your notes, it's easier to read than it is on my PowerPoint. So a system can exchange energy with the surroundings through heat and work, which makes sense because we just said energy is transferred through heat and work. So a system can exchange energy through heat and work. So for whatever reason, heat is given the symbol little q. I wasn't there for that meeting. I would have had them pick a different letter. Maybe they felt there's not a lot of q's out there. Maybe we'll go because work got the W. So our first law states that our change in energy, our change in internal energy, must really be the sum of heat transferred which is our Q, and work done. Right, because if all the energy is equal everywhere, and the only two ways we can transfer energy is through heat and work, then if we have a change in energy, it must be a change in heat, change in work for the system. So mathematically, we write this way. So any change in work between two states of matter or a chemical reaction is directly related to the heat transferred, Q, and the work done, W. So let's see if I can focus that a little bit. Oh, that's a little bit. Alright, so Q, our heat. If we have a positive Q, that means that the system has gained energy, thermal energy, right? It's getting hotter. If it's a minus heat, it means that it has lost thermal energy. It is getting colder. That should make sense. Plus hotter, minus colder. For work, if work is done to the system, so you do something like change the pressure or change the concentrations, that is a positive change in work. If you have a negative change in work, it means that the system has done work on somebody else. It's given away some of its work amount to do work on somebody else. So then if we have a positive heat, positive work, it means that energy is coming into the system. If we have two negatives, it means that energy has been leaving the system. Good there? All those definitions make sense so far? So do I have this page? I'll just write on the back of this. So here's my example. Does anyone out there play bocce? No. Lawn bowling? Bocce ball? One person will understand my example then. Everyone else will have, imagine bowling, but on the lawn. That's pretty much bocce. can instead say, let's imagine we're playing pool. That's fine. The example works out the same. I just prefer bocce over pool, so I picked this one. When you guys get a turn to teach the class, then you guys can pick your own examples. So it's my turn. I'm going to test the ball with a given amount of kinetic energy. You guys ever watch curling? It's very similar to curling. Bocce and curling are similar in that there's a center spot or a center ball that you're trying to get the closest to. So you can either play offensively by just getting your ball closest to the target, or defensively by hitting everyone else's ball out of the ring. And thereby you have all the points, now the opposing team has 0 points. So 2 ways to play. I like to play defensively. I like to hit everybody else's ball out of the way as hard as I can. Mostly because my aim's not great, but I know I can knock them out of the way. That's about it. Alright, so I managed to hit the opposing team's ball, which in this case is a good thing. And my ball transfers all of its kinetic energy, which is all of its motion energy, to the second ball. So the total change in energy from my ball is going to be the difference between initial and final kinetic energy. Then we can talk about the amount of work energy done. So because this is lawn bowling, the work done by my ball on the second ball is going to depend on the lawn that you choose to play on. So, you can imagine this like a putting green, right? The smoother the putting green, the straighter the ball typically goes, less friction, whatnot. If you have a not well-maintained putting green, you have to hit it typically a little harder, or if you're at the putt-putt, right? With its AstroTurf, it usually looks like this. You gotta hit it a little bit harder to try and overcome the issues with the AstroTurf, or whatever they use at their thing. So as my ball rolls across the lawn, it loses some of its kinetic energy because it's giving away the friction. Right? This is turning kinetic energy we are losing some of our kinetic energy to really heat. So, the amount of work right? So if you're on a real smooth lawn, less friction, the amount of work I can do on the second ball is greater. If it's a real rough lawn, the amount of work I can do, my ball hitting the other one, is going to be less. And a lot of it comes down to the fact that I'm giving away some of my kinetic energy to heat. So the amount of heat and work depends on the lawn. That is not a state function. So if I did the exact same thing on two different lawns, I would get different results. The kinetic energy I was able to give the ball in the very first place is a state function. And so I have some kinetic energy I gave to it. Either it gives it away through friction and a few other processes, or it doesn't. And so the final kinetic energy in both cases is 0, because I gave it all the way to the second. There's also a snazzy picture, if you're more of a picture person. That exchange energy. This one's also from your book. So in this case, I have an initial kinetic energy. Oh, you can't see that. Initial kinetic energy of 5 joules. In this case, it loses some to friction, which means the kinetic energy is 4.5. Because I had 5, I lost half of 4.5. And the kinetic energy after collision is 0. So I was at 5. You lose all 5. So delta E is a loss of 5. That makes sense. In this case, I'm on a really rough pool table. So the same thing. I still have 5 joules when I hit it. In this case, I'm giving much more away to friction. I'm giving away 3 joules to friction. Which means I only have 2 joules of collision left over. But still, I started off with 5 and I end with 0. So in both cases, regardless of the friction issue, the difference in kinetic energy is 5. You guys look super pumped today. Is it just like one of those days where you're like, I can't believe I'm in this class, I'm so excited, tell me more? No? Not one of those days? Alright, we'll do one last topic then. We'll do heat. So, heat is the exchange of thermal energy between a system and its surroundings. How do we typically measure heat? This should be a gimme. What sort of temperature, right? What physical instrument do you use to measure temperature? Thermometer, good. Just making sure everybody's conscious. Good. Whoever had lab this week with Ms. Oslam, she said you guys rocked it out on the molecular model kits. She said she wanted to specifically tell me that this class knew their junk talking about molecular model kits and how to do those things. So, good job on you guys. She's very proud. Very proud. So, side note, really had nothing to do with this, but made me think about it. Alright, so temperatures are a measure of thermal energy. And heat is going to be our transfer of thermal energy. And thermal energy is always going to travel hot to cold. So that's going to be our directionality of heat. We will save heat capacity. Has anyone ever done coffee cup calorimetry? A few people? Good. We're going to do it again next week in lab. But we're getting us all caught up so we all talk about heat capacity, cup calorimetry, how to measure the heat released from a reaction. Can we do it?